Okay, now I hope you can hear me. Hello, everybody. Welcome to our active lecture for Monday, the 15th of June. Couple of quick announcements. I should have written them down. I'm trying to figure out which homework I'm on now. I believe it's the 4th homework, one that's due today. Lost track. Yeah, 4th homework. Phew. Okay, 4th homework is due today at 5 p.m. I have office hours because I've got a 4:30 meeting and you might need help before they do. I'll have office hours from 3:30 to 4:30. But if you need some extra help outside that time window, let me know, and I'm happy to chat with you. The first exam is graded and posted. The solution posted online. Let me know if you can find them. They're attached to the end of Module 5.
Professor?
Yeah.
I actually checked your Module 5, and I think you might have accidentally put a Homework 2 solutions.
Oh,
when I clicked the link.
Oh, they're the wrong solutions?
Yeah.
Right. Okay, that's why okay, hold on. All right, I will fix that. I can't fix it right now, but I'll fix it immediately after class, okay? I know people want to see the solutions, so. The main thing people got tripped up on for the exam is the issue of problem 1, where you're coming around the curve, and there's the car right there. Most people correctly noticed that there was an acceleration on the car and it was in the centripetal direction. But a few people got confused about friction. In this problem, the force of friction is not pointing this way or this way. It's the force that's keeping the car on the track. If it wasn't for friction, the car would go perfectly straight. So that's something I want to talk about today. All right, so I'll fix that posting problem. I'm not sure how I did that, but I'll fix it. Oh, I know what I did. I probably saw a solution. Okay, the file is there. I just have to put the right link in, I guess. Then these are the topics we're going to talk about today. Okay. So I will post those solutions right after class, so you can see them. And if you have any questions about how I scored your exam, I posted on an announcement about the grading scale. Basically, if you're in the mid to upper 80s, that's A land. B land is from the middle 80s down to this middle 60s. And almost everybody basically falls into that category one way or the other. And again, the exam's worth 5% of your grade or 10% if it makes your grade better, whichever one is best for you. And if you get tripped up and you want to check with me about anything, by all means, send me an email and we can set up an appointment. Okay, so first thing to do today is to go back just for fun, Newton's first law. Just to remind you, what does it say? It says if the net force on a body or system is equal to 0, then the velocity is equal to a constant. And you might reasonably ask the question, why do I need the first law if for the second law I can derive this from the second law? What was Newton's purpose in writing this down? And the reason he wrote this down is because he wanted to define, not because you couldn't derive this from the second law, but because he wanted to start by defining what we would call the basics of natural motion. And it's important to realize that as to what was going on when Newton came around, there had been hundreds of years of what we call Aristotelian Greek physics, which had a certain notion of natural motion. And that notion is very simple, that things naturally fall, right? So if I have an object and I let it go, it falls down. And the answer is, the question is, why does it fall down? And if you're Aristotelian, to say the reason it falls down is because that's natural. That's what things do. They fall down until they hit something, right? So until it hits my hand, and then it stops falling because it's as far as it can go. And then if I toss it, if I take something and I throw it, like, over there, I watch it for a while and it comes to a stop. Why does it come to a stop? Well, because that's what things naturally do. They naturally come to a stop. What Newton says is that in the absence of forces, the natural motion of something is to go in a perfectly straight line forever, which is quite counterintuitive, and at least counter to your ordinary experience. Most objects, you don't have no net force on it, so the object will tend to slow down. Why? Because there are forces on it. And that's what comes into play in this first problem on the exam from last week. The car, when I'm going around the curb, even if I'm not speeding up or slowing down, there has to be a force on me in order to make me go into a curve. If I wasn't, then I would go in a straight line. And when you make a free body diagram, and by the way, if you didn't make a free body diagram for problem 1 part C, that's sometimes where you got tangled up. But if you do the free body diagram, up is normal, down is weight, and the only force that could possibly be applied horizontally is friction. So here's the way to think of it. If you're coming into a curve and the road is glare ice, and there's no friction, what will happen to the car when you try to turn left? It'll just go straight off the road. It's the friction that keeps you on the road. Okay, so Newton's first law. Ask yourself, when you're not sure which forces come into play, ask yourself, what is the motion, uniform circular motion? What's the acceleration? And therefore, there must be a force in that direction. You said the force of friction was 0 because it was not speeding up or slowing down, because there was no slipping or no sliding. Then you weren't thinking about the second law. You were thinking something else. All right. So that's all I want to say about that. The next thing I want to talk about today is just a quick context of conservation of linear momentum. And remember, the key issue is that there's a condition. If the system is isolated, which is just code for the net force is equal to 0, then linear momentum is conserved. So then P tot is equal to P tot prime. Okay. So we looked at one example of this, which is the first real example we're going to look at for now, which is a totally inelastic collision. This basically, translates to, MA VA plus MB VB. If I have a collision, let's just write the collision here. So I've got two blocks, A and B, and they're colliding, and that's equal to MA VA prime plus MB VB prime. And then if it's totally inelastic, which is to say sticky, then I have the additional constraint that VA prime is equal to VB prime. So these two equations, if I give you the initial masses and velocities, these two equations let you find the final velocities and the final velocities, since they're both the same. If they're totally inelastic, they stick. So let's look at, now that we have this concept, let's look at some problems that, let's just look at a kind of basically a variation on a theme here. So that's for a collision. Suppose I have something which I'm going to call an explosion. So here's the idea. I've got, say I've got a brick. So this is a brick. Inside the brick, for devious reasons, I put a firecracker, which is to say a small piece of explosive material. And I detonate the firecracker. So this is before. So on a brick, no friction, and I detonate the firecracker with somewhere inside, right? So, you know, before V is equal to 0, nothing's moving. And then after, I got the brick miraculously breaks into only 2 pieces, somewhat miraculously for the purposes of doing the problem. So there's 1 piece there, and then here's another piece here. So 2 pieces go flying off, right? So this will be, I'll call this piece MA and this piece MB. They have, I tell you the masses, and the question is, if I give you the velocity VA, can you find the velocity VB, right? So given MA, MB, VA, find VB. That's the problem, right? So, you know, some kind of explosion happens, the 2 pieces go flying off. How do I tackle that problem? And the conceptual key to this problem is that, so this is the before, and again, this is the after. So I can't use, let's just go through the menu of things we can consider. It's not a kinematics problem because I don't have position as a function of time or anything like that. It's not that you can apply Newton because you have no idea what the force is here from this explosion. That's not on your menu. You cannot use conservation of energy. And the reason you can't use conservation of energy is because the forces here are unknown and not necessarily conservative. And in fact, if you think about it for just a second, it's obvious that you can't use conservation of energy. What's the total energy of this system? The brick sitting on the ground, it's not moving, so the total energy is 0. What's the total energy of this system? Well, the potential energy hasn't changed, but the kinetic energy has changed. The reason you can't use conservation of mechanical energy in this problem is because the energy that's stored in the firecracker cannot be written down in terms of mechanical energy equation. I don't have a means, and it's a chemical potential energy, but I don't have a way to write it down, so I can't use conservation of mechanical energy. So the only thing that's left is conservation of linear momentum. Can you use conservation of linear momentum? Well, there's no friction on the system, which is a brick, so that's nice. The vertical forces cancel out. The system seems isolated here. What about? Well, there is an explosion, and you don't know what those forces are. But the happy news is that the explosion basically is a force that basically is applied within the system. In other words, whatever the force is of that firecracker, it's pushing out in all directions. It's internal to the system. The firecracker was embedded in the brick. So those forces are internal. They're not external. So the system is isolated. And I can use conservation of linear momentum, conservation of linear momentum, right? Conservation of linear momentum. P tote is equal to P tote prime. Well, in this case, I know what P tote is. It's just the mass of the system times the system, which is 0. So that means 0 is just equal to PA final plus PB final. So I won't put primes on them because they're the only examples, right? And then, of course, then I can plug in MA and MB into this, right? So 0 equals MA BA plus MB BB. And everything I know is in terms of things I don't know. So, I mean, the other way around. BB, I just solve for BB, and that's just equal to MA VA over MB, which is a pretty familiar looking result. So notice something here. If I run this movie forward, notice something about conservation laws. Conservation laws involve terms that don't depend on time. That's kind of the idea. Whatever the quantity is, it's independent of the time. So I can evaluate it on either side independent of the time. So in this case, if I run time forward, I have a brick that explodes into 2 pieces, right? But suppose I run the movie backwards. Suppose I had a film and I ran the movie backwards. What would it be? Instead of seeing 2 bricks going out, pieces of the brick would come in, and they'd form the original brick. In other words, the movie would go like this, whoop, they'd stick. So running this movie backwards is the same as a totally inelastic collision. And all that means is that I've done before and after, and I've switched them. So an explosion, any explosion, is essentially the functional equivalent of a totally inelastic collision with the movie running backwards. So you can use the same equation. Time doesn't matter whether I go before, either side of the equal sign is fine. Okay. Now let me say something. Suppose here I've got this object, and if I was doing this in class, I would have a volunteer step up, and I would ask the volunteer to toss the fuzzy object to me, and I would catch the object. So if I catch something, say something's tossed to me, here it comes, whoop, and I catch it. What does it mean to catch something? It means that the object was coming towards you, and it came into your hand. Yes. So now it's in my hand. It's stuck. If I catch it, it's stuck. So anytime let's decode some physics words here. Anytime I catch, that's the same thing as stick. So that's totally inelastic. Well, what if instead of catching, I throw? Okay, so here I'm going to go, I threw it. That's, what is that like? So anytime I throw, that's the reverse of stick. So that's the functional equivalent of an explosion. So that throw means explode. Okay, so catching and throwing are just totally inelastic collisions and reverse collisions. Okay. Now, one thing that's important, we have to keep track of whether the system is isolated or not when we charge ahead and do these problems. So let's do a problem. Okay. So, person is standing on the surface, and there's a ball. So the person's mass is big M, and the ball's mass is little m, and the initial velocity of the person v equals 0. And I have another ball that's basically coming in like this with some velocity, which I will say is equal to v, little v, which we'll define as, I just don't have quite enough space here, so let me just do it slightly different here. So I'll say this is little v, which is defined as v0. Okay, so big M, little m, v0 given. Okay, person catches the ball. I'm only going to worry about the horizontal motion. So there's maybe some vertical motion going on with this ball, but I'm only worried about the horizontal motion. Which is fine because in principle you can apply the laws one coordinate at a time. And I want to know what is the final velocity. Okay. So it's a catch, right? So the ball comes in, I catch the ball. What's my final velocity? So there's a piece of information that's important in this problem that I haven't told you. What is that piece of information that you critically need to solve this problem? There's a detail we need to understand. Anybody? Any ideas? We need the mass, the velocities, person standing. In general, if you're standing there and somebody throws a baseball to you, you're playing baseball, and you catch a baseball, you stop, you caught the ball and you stop, what's your final velocity? What do you see your final velocity is? Anybody who's just catching a baseball. 0, right. Why is that person's final velocity 0? What's the critical thing that causes that person's final velocity to be 0?
Do they apply a force to the ball?
Well, they caught the ball. So when you're standing, here's the thing. When you're standing on the ground and you're catching a ball, is the system, here's my question, is the system isolated? We have to, in other words, if I'm going to apply conservation of momentum, I have to answer this question. Yes? So if I'm standing on a baseball field and I catch a ball, is that in an isolated system? Now you might say, well, yeah, it's isolated because we're going to ignore the vertical forces. We're only going to consider the horizontal forces. And when I'm standing here, just standing here, by definition, there's no horizontal force on me before I catch the ball. And if the ball is moving at constant speed, there's no horizontal force on the ball. It's already been thrown. So you might say, oh, this is an isolated system because at this instant before I catch the ball, there are no horizontal forces on me. But as soon as I catch the ball, my feet on the ground have friction, and it's that friction that holds me in place and keeps me from basically ricocheting off to the left. In other words, if there's friction here, then that friction, even if it's not in play before the collision, it could be in play during the collision. So this system with friction is not isolated. In general, if I give you a system and there's friction that could come into play anytime during that collision, the system's not isolated, and you can't use conservation of momentum. That doesn't work if I'm standing on the floor or the grass or the ground, or I'm a car with tires. Anything where there's friction that could come into play during the collision invalidates the application of, it basically means the system is not isolated, and therefore you can't use conservation of linear momentum. The only way I could use conservation of linear momentum in this problem is if I told you that the person was standing on ice or something where there's essentially no friction. No friction. If I tell you this, then for no friction means that the system is isolated. Yay, at least in the horizontal direction. And then what happens? Well, then the person catches the ball, and again, the total moment, this is a collision, right? So it's a totally inelastic collision. So I have, I can write down p total equals p total prime. The initial momentum is equal to mv naught, the little m, little v naught this way. The final momentum is also little m, little v naught this way. So after I catch the ball, if I'm standing on ice and somebody tosses me the ball, I catch the ball and then I continue to move backwards. I move back slower because now the total mass of the system, m plus m, times my new velocity, which is v prime, has to be equal to little m, smaller mass, times the original velocity. So I slow down. I mean, I don't move as fast as the ball was moving, but I still move. As soon as I catch that ball, I start to move in that direction. Does that make sense? So I can only, this is so important, I can only apply this rule, p total equals p total prime, if the system is isolated. By the way, suppose I throw, let's do the opposite experiment. Suppose I've got a baseball or something and I throw it. What's my final velocity after throwing it? There it goes. Have I gone anywhere? No, I'm standing still. Why am I standing still? Because I've got my feet on the ground and I'm applying friction. In fact, if you think about what a baseball player does when he throws the ball, they dig in with their cleats so that they get the maximum amount of horizontal friction, whatever we're going to call whatever the force is, that's horizontal friction, the maximum friction, that feet don't slip or slide, to give the most force possible without them flying back at the same time. But if a baseball player tries to throw a ball on glare ice, the ball will go this way and they will go that way and the total momentum will be conserved. Isolated or not isolated, you have to check. Okay, questions about that? All right. Okay. Let's try, let's look at something else. We did a little bit of discussion earlier about where conservation of linear momentum comes from. So let's just write this down again. Everything derives from Newton's second law, which we said, just to remind you, F equals ma, but we also said that that's the same thing as F equals the time derivative of the linear momentum, dp dt. These are two alternate ways of basically, this is a net force. Two alternate ways of writing down Newton's second law. So once I've written this, I can do a little bit of kind of simple calculus. I can write that, I can basically bring the dp over here and then leave the dt, basically do the cross multiplication. So in other words, I can say dp is equal to F net, the net force, times dt. And then if I want, I can integrate on both sides. So if I integrate over some time interval that's changing, then this basically corresponds to the change in the momentum. So we'll call that delta p. And then this thing here is just an integral over time of the net force times dt. So this thing has a name. Delta p is defined as the impulse. If you're reading a physics question and anybody asks you what's the impulse, all that means is the change in momentum. So impulse doesn't make sense unless the momentum is changed, right? If a car, if there's a collision and a block changes from one speed to another speed, the impulse is the change in momentum, okay? What about this integral here? Well, this integral here, so the statement, by the way, delta p is equal to the integral of F net delta t, dt, that integral. This statement has a name. It's called the impulse momentum relation. And one other thing you could sort of say is, well, if I'm taking an integral of a quantity over time, that's the same thing as basically multiplying the average times that time interval. So you can also say that delta p is equal to the average force. It's a way of basically, even if you don't know the actual details of how the force is evolving, you can just say that's at the average force times delta t. All I've done is use the basically a fundamental calculus relation that says any function integrated over an interval is just the average of that function times that the length of that integral. So this may be useful for solving some problems if you measure the change in momentum. Remember, what do we mean by the change in momentum? We mean the final momentum minus the initial momentum, so p prime minus b. And if I know the delta t, I can work out the average force. Even if I don't know anything else about how the force evolves, I can do that. So this is called the impulse momentum relation. And it's a nice relationship because it's a quick way of solving certain kind of problems, even though, and the other nice thing about it is that you can use this. If you know the initial and final momentum, you can use this to calculate the average force, even if the forces are not conservative, even if the system is not isolated. This is always true. It's never not true. It's always true. Okay. So likewise, and I've sort of alluded it to in your homework and on the review sheet, but I haven't actually explicitly talked about it. There's a similar relationship called the classical work energy relation, or sometimes called the classical work energy theorem. And that says, well, without going through the details, that says that the change in kinetic energy is equal to the total work. And just to remind you, so that's the total work, delta k, the total work is defined as an integral on a path of f dot dt. And in this case, the total work is just the sum of all the works. The sum of the integral being the integral of the sum, then that just means that the work, that's the same thing as the work done on a path, again, of the net force. And again, delta k is just k prime minus k. So again, k prime minus k is equal to w tilde. This is just a third way of writing the classical work energy relation. All these statements are true. And again, the wonderful thing about this is that this is always true. It doesn't depend on the force being conservative or not. If I can calculate the total work, I know the change in kinetic energy. If I can see the change in kinetic energy, I can calculate the total work. So these two relationships, the classical work energy relationship and the impulse momentum relationship, these are known as bridge. I call these bridge concepts because they bridge the realm of Newton's laws, which is to say forces, to the realm of conservation law, which is to say energy and momentum. And notice they have very similar form. Basically, a change in a quantity that's related to conservation. So here, kinetic energy, here, momentum, is equal to some integral of the force. This is not right. This should be dr. That's important, and that's a dot product. So here, the integral is the work is the integral of the force on a path. So I'm integrating a force over. The way to think of it is I'm integrating on a path, so that's a force integrated over a distance. Force times distance. Here, the change in momentum is equal to the integral of a force over time. Again, force times time. So force times time is the change in momentum. Force times distance is the work, which is the change in the kinetic energy, right? And again, both of these expressions can always be used. You can always use these things. So let's look at some quick examples. So now that we have this in our pocket, let's just do some mental, simple exercises to think about how we use this. All right, so, and this is a participation one. So you remember the plus, minus, zero, doing the same thing, positive, minus, and zero, okay? So if you're ready, so if you put your mic on and then we all participate, we will have a thing. So suppose I have this eraser in my hand, and now I'm going to take the eraser and I'm going to move the eraser up with my hand like this. Whoop. So I'll do it again. Start here and move up here. Whoop. Big before, moving after. Okay, when I do that, consider the work done by the force normal on the eraser due to my hand. The work done on the eraser due to my hand. Is that work positive, negative, or zero? Anybody? What do you think? Start here, move up here. Work done is positive, negative, or zero by the normal force on the eraser. And anyone want to volunteer?
We'll say positive.
You'll say positive. Why would we say positive?
Because the normal force is pointing up and the eraser is moving up.
Great. So we know that the work is equal to this kind of thing, and if the force is constant and the deflection is straight, which it approximately is here, then that's going to be basically the magnitude of the force dotted with the displacement, delta, well, in this case, delta y, right? And that's a dot product, which means that there's a cosine. So that's F delta y, whatever the normal force is. So we're talking about the normal force here. The normal force times delta y, and then cosine at the angle. The normal force points up, and delta y points up, and so I get positive, positive, and 1, and that's a positive work done. That's the work done by the normal force. It's positive. Good. Same thing. I go from here to here. Start. Stop. Okay. Work done by the force of weight. Positive, negative, or zero?
Negative.
Negative. That's right. Why negative?
Because it's moving it. I mean, you can use the same logic, but y is in the opposite direction. So
Right, exactly, right. So the work associated with the wave force, basically the same logic, but now the wave force is pointing down while the displacement is pointing up. So in the normal force, notice something. So now let's do this. Suppose I take the eraser and I move the eraser from here to here. So what I did, I picked it up and I moved it from here to here. You can hear it moving. Okay. Work done by the normal force. Positive, negative, or zero?
0. Right.
0, right. Because in this case, when I go from here to here, the normal force is out of the board, and the displacement is this way, so they're perpendicular, right? So perpendicular cosine, that's 0. Good. What about same path, same story? Eraser goes from here to here. What about the work done by friction on the eraser? Positive or negative or 0? So I go from here to here.
Negative.
Negative.
Negative. Right. So if I go from here to here, there's a force trying to keep the eraser from moving. So there's a force on the eraser. If I'm pushing on the eraser this way, there's a friction force pushing the other way. The friction is in opposition to the motion in this case. And so the displacement is positive. The force is in the opposite. So the work done by friction is negative. So in this case, I go from here to here, the work is negative. What happens if I go from here to here? I'll do it again, from here to here. Work done by friction, positive, 0, or negative?
Still negative?
It's still negative, that's right.
Because
Why?
you're still moving, well, you're moving just in a different direction, but the friction is still opposing the direction.
Right. So when I went from here to here, the displacement was this way and the friction was that way. When I go from here to here, the displacement is this way, but the friction that way. So friction, yeah, friction often, so that tells you right away, by the way, that the friction cannot be conservative, because if I go like this and this, I've done negative work by friction, and it doesn't go back to where it came from. Okay. All right. One more. I'll do the same thing on the chalkboard here. So again, start here, end here. So I'll go like this. So start now. That's start. Stop. What's the total work done on the eraser?
0.
0. Why?
Because you're starting at rest and ending at rest.
Right, exactly. So in other words, here, K, which is my initial velocity, is 1/2 mv squared. As long as I tell you, as long as you can see, it's not moving. And my final velocity, so that's 0. And then my final velocity, v prime, is also equal to 0. So K prime is equal to 0. So I can tell, in other words, I don't have to calculate all the works to figure out the total work. All I have to do is notice the change in kinetic energy. Suppose I'm moving across the board at a constant speed. And as I move, this t equals 0. I'll call this t naught, or we'll call it x naught, for position x naught, and we'll call this xf. So constant speed. What's the total work done on the eraser as I go from here to here?
Is it also 0, or am I wrong?
Let's watch it again. So I'm going, as I go past here, I have velocity v, which is constant. As I go past here, I still have velocity v, which is constant. So K is not 0. It's equal to 1/2 mv naught squared. And here, but here K prime is equal to 1/2 mv naught squared. So again, no change. And therefore the total work is 0. Total work done is equal to 0. We know that the work of friction is negative. That means the force of normal that I'm applying with my thumb in this direction must be doing positive work. And if we can evaluate the force of friction over that distance, we can evaluate the negative work done by friction. We can therefore evaluate the positive work done by normal force. But the two must total to 0. One last one. I got my hand here, and I go up like this. Total work done?
0.
0. Yeah. Now, suppose I take my eraser and I've got it in my hand, yes? And then I apply a force on my hand so that it goes up in the air and comes back down and I catch it. Total work done?
Is it still 0?
Still 0 because I started at 0 and ended 0.
Yeah.
Okay? And by the way, I can now do this. Suppose I take the eraser, I've got it in my hand, it's at rest, and then I throw it at a funny angle. It bounces off the chalkboard and lands on the ground. It bounces several times and comes to rest. Total work done?
0.
Still 0, yeah. It's magic. As long as you know the initial and the final velocity, it doesn't matter how many forces, what direction they apply in, how long they apply in, and what direction they, as long as you have an initial and final velocity, the difference between the kinetic energies is the total work done. Kind of amazing. All right.
Wait,
So,
question.
yeah?
But when it landed on the ground versus your hand, there's a change in height. So
Yep.
what does that mean?
Okay, well, I'm glad you asked it. So I start here, I toss it in the air, and it lands, okay, it lands down there, and it bounces. Yes? So when it hits the ground, now, by the way, just before it hits the ground, is the velocity 0? Just before it hits the ground.
No.
It's going down. So in that case, there's work done. In that case, the kinetic energy is not 0. In fact, the final energy, if I choose the final moment, the instant just below I hit before I hit the ground, in that case, the final kinetic energy is positive. That means the change in potential energy is positive. That means work's been done. Where did that work get done by? Well, most of the work was done by the fall of the object as it went down, by the force of gravity pushing down. But when the eraser hits the ground, hits the shag carpet, right? What happens is there's a force back up, right? That force slows it down. And then, of course, it goes up and bounces a few times, so there's a bit more forces being applied. But at the end of the day, there's forces normal being applied to that eraser to stop it. Yes? And those forces are doing work, how can I put it? They're basically slowing it down. So even though gravity sped it up, the normal force is slowing it down. Gravity doing positive work, normal force is doing negative work. All together has to total to 0.
Got it. Thank you.
Yep, it's a good question. All right. What have we got time for? I think I'm mostly done. I don't know if I'll have time to do that path integral example. We can set it up. So the bridge concepts are great because you can use them anytime you want, and they give you a shortcut to the answer sometimes, especially if I ask you for the total work, or if you could work out the impulse, then you don't have to use conservation knowledge. You can just skip to the bridge concepts. All right, so one more thing, and that is I want to get people used to actually working with the path integral. So we warmed that up a little bit with the lecture before class today, which said that if I want to calculate the work associated with a particular force F, that this is the integral on a path of F dot dr. And if I have the components of the force, then I can basically write this down as break this into two one-dimensional components, f of x dx plus the integral of f of y dy. And I'm integrating from, if I'm going from some point P to some other point Q, then the limits here are x sub P and x sub Q, and this limit y sub P and y sub Q. So this is one way of sort of tackling that integral. So let's actually apply it to one or two quick examples. This is sometimes the word overkill, but it's something that we've done before. If I want to know the work done by the force of weight, right? So how do I deal with the force of weight? So this is W, the weight. So I'll label it weight to be clear. How do I write that down as a vector expression? Well, it's a force that applies downward. So, here I'm going to have my usual x and y this way. So there's no component in the x direction, so it's 0 I hat, plus whatever the force downward. Well, we know the magnitude of the wave force. It's mg, but it's minus because it's pointing in the negative j hat. So that's a vector representation of the wave force. And if I just ask you, well, what are the components of that force? Then I can say that the x component is equal to 0, and the y component, w sub y, is equal to negative mg. So if I have a path where I'm basically going from some point P to Q, so here's P and here's Q, and P corresponds to x sub P, y sub P, and Q corresponds to x sub Q and y sub Q. And I'm taking some path. I don't know what the path is. It could be complicated, right? But if I want to know what's the force, what's the weight, I can use this expression to explicitly calculate what that work is. So I can basically say that the work done as I go from P to Q is just equal to this term, which is, you know, that term there, f of x dx. Well, f of x, so in this case, what do I mean by f of x? So in this case here, f of x is just equal to wx, which is equal to 0, and f of y, which is just equal to wy, that's just equal to negative mg. So in this case, the integral of 0 is 0, so that's just 0, plus I should have written this here, plus the integral of this term here, f of y, which is just negative mg, that thing, dy. And the only issue is, where do I integrate from? I integrate from y sub p to y sub q. Okay, so that means that the work, well, this is an easy integral. It's just mg y plus, but then I've got the two limits here, so that just becomes basically m g times y sub q minus m times g times y sub p, right? Which is just the same thing as, sorry, I went out of room, which is just mg, negative mg of negative this, negative all this. So that just becomes mg times the change in the height, which is just y. So wait, no, careful. I'm going from, I go from A to B, so I take B, yeah, exactly, usual story. So I end up with negative mg yp. I'll just stick with this negative sign here, minus yq. Okay, so that tells you the work that's done. If I go from here to here, if yq is greater than yp, this is positive and that's negative. And we have the rule that says that the potential energy U is equal to the negative of the force. So it's the negative of the work done. So in that case, that's just equal to, you know, the change in potential energy is just equal to a negative of this, which is just mg times yq minus yp. Okay, the negative sign goes away. So this is a one-dimensional force. It's easy to do the integral, but you can see the method basically works. I just break it into components. Let's do another force where we can actually work out the potential energy, and that'll be the last thing I think for today. Yes, pretty much. It's easy to make sign errors, but you can check at the end if it's positive work or negative work, and it makes good sense. So I'm going to leave this equation up here because I'm going to use it. I'm going to introduce a new force. This will be another force on your force menu, which is the force associated with the spring, which is called Hooke's law. So the way to introduce the force of the spring is I have here some kind of surface. So we'll call this the floor. We'll call this the wall. And I'm going to attach something called an ideal spring. Where it is, boing, piece of metal. And I'm going to attach it to a mass, m. And I'm going to displace the spring from its equilibrium length. So if the spring was unstretched, it would basically come to this distance, but I'm going to stretch it by distance basically corresponding to, you know, the object basically being stretched by that much. So I stretch the spring by x from equilibrium. So equilibrium, or from, I won't use the word equilibrium, I'll use from relaxed. So in other words, a relaxed string, so relaxed is better than equilibrium because it means something more specifically. A relaxed spring is neither stretched nor compressed. Okay? And Hooke's law says that the force applied by the string, its magnitude, is equal to some constant k times the displacement x. Except for there's a, how can I put it? There's a absolute value sign here because this is a magnitude and k is basically, if I stretch the spring, I get the force. If I compress the spring, I also get the force. And the only rule is that it basically points back to x equals 0. So in other words, the force that results by stretching a string in this direction is a force that basically applies in the negative direction, and I'll call that F of spring. Okay? So I have an expression for the force. I know what kind of force is it? We're calling it the spring force. Spring force. Spring force. It's a known force in the sense that I don't have to calculate it using Newton's laws. I know what it is. As soon as I tell you the displacement, I know its magnitude. So the farther I put that block here, the stronger the force of the spring pulling back, and it's linear. And this thing K is called the spring constant. It's just a constant that, generally speaking, will be given to you. And it basically has to do with how stiff the spring is. The bigger K is, the larger the force. And therefore, for the same displacement, the larger the force. So a wimpy spring will give you a low force. A stiff spring will give you a strong force. So that's a new force that's on our course menu. It's now known. It's a contact force in the sense that it depends on being in contact with the spring. So I have that force. What can I say about the potential energy of that force? Well, the potential energy associated with the spring force is just equal to the integral of the spring force dotted with displacement on a path. So that's a path. So the happy news is that this is a force that is applied in that particular direction. So that means I can figure out what the dot product is between the displacement and the path. So if I have a displacement in the positive direction, if this is my displacement, x, then the force, F spring, is basically applied in this direction, in the answer direction. So the dot product, yay, the dot product means that sorry, this is the negative because I'm doing the negative of the work there. So the dot product gives you another negative sign. So in other words, the potential energy is basically, this is the negative of the work. So that's the negative of the spring force, which is just the x component of the spring force. And that's the only component, right? That's F of x, right? This is 0 for the spring force. So it's just this first integral I need to do. So that's the integral. So that's just the integral of the spring force dx. And I'm basically going to integrate from the, pick my reference point to be x equals 0 to x. And then this is basically primed in the sense that I want to basically do the integral inside. Okay? So let's do that. So I say, okay, I know what that is. So that's the integral, negative of the integral of kx, right, which is the magnitude of that force, kx. But again, in this force is now being applied in the negative direction. So that dot product gives me the negative sign there. And then this is just the x, and I go from 0 to x. So this is, well, that's an easy integral. That's the integral of x, basically 1/2 x squared. And then two negatives, they cancel. So I end up with 1/2 kx squared. That's the potential energy associated with the spring force.
Professor,
Yep.
can I ask why there's a negative sign in front of the path integral?
Well, because remember, this is the definition of potential energy, which is equal to the negative of the work that's done.
Oh, okay. Okay, thank you.
Okay. As I go from P to Q or whatever it is. So yeah, I often, that's why I said, oops, forgot the negative sign. That's where it goes there. And then you see it needs to be there because this is a positive potential energy. As I stretch the spring, I'm doing, the way to think of it is, the spring is doing negative work. The negative work that's done gives me a positive potential energy. I'm putting energy into the spring. If I let go of the block in the spring here, if I let go of the block, it comes flying back. That potential energy is converted into kinetic energy. And by the way, this integral sign, if you really want to do this absolute sign, if you want to change x to negative, then that negative goes away, but that negative comes in here, and you end up still with this answer. So this is true for any x.
Okay, thank you.
All right. Cool. So now we have another force that is, by definition, because we've calculated a position that only depends on its a potential energy that only depends on its position, and therefore is path independent. All I care about with the spring is where it is. That tells you the potential energy. So now I have a second potential energy for doing new potential energy problems, new conservation of energy problems. I have a new conservative force. So if I say, let's calculate all the forces we have weight, normal, tension, friction, and now we've added the spring force. That's 5 forces. Also the applied force, but remember, please, please, please do not put the applied force on any problem unless I give it to you explicitly. You can't invent the applied force. So let's do it again. Weight, normal, tension, friction, and now the spring force. Which of those forces are conservative? The only forces that are conservative are the weight, where the potential energy is mgy, and the spring force, where the potential energy is 1/2 kx squared. Okay, that's all for now, for today. I'm happy to stop and answer questions about homework. I've got office hours starting at 3:30 if you want to questions then. I'm trying to catch up on grading the homework. That should be done hopefully by the end of the day. There was one other thing I wanted to mention. Oh yeah, there's only one more. We've got those 5 forces for physics 121. We'll only add one more force, and that's the force of universal gravity, which we will also calculate the potential energy for. It turns out it's also conservative. And that's all I have to say for today. All right, questions? Questions about bridge concept, conservation of linear momentum, anything about the homework that's due today? Everybody's happy with the pendulum problem?
Do you mind talking a bit more in depth about like the bridge problem? I mean, sorry, the bridge concept between.
Well, which between there's 2 of them, right?
Yeah.
I'm gonna erase this. That's okay.
Mhm.
All right. So the problem, of course. So we're going to do an exercise in class tomorrow, which I entitle "Name That Concept." I'll break you into groups tomorrow, and the question is which concept do you apply to which group? So the bridge concepts are, so far there's 2 of them. We'll actually add a 3rd when we do rotation. So the first bridge problem concept is I call, just to write it down, is the classical work energy relation theorem. So by the way, there's more, depending on your favorite textbook, there's 10 different ways that people name this thing. So I will usually call it classical work energy theorem, so just CWE. Or sometimes you call it the work energy relation. So sometimes it'll just be work energy relation, WER. Sometimes it's just called the work energy equation. People call it all kinds of things, but that's what it is. And it basically says that delta K is equal to W tot, the total work. And it's always true. And it turns out that this can be derived. I haven't derived it, but it's quite straightforward to derive this, starting with Newton's second law and the definition of kinetic energy and the definition of work. Okay? And it turns out from this is the basis upon which we actually calculate, we'll actually write down conservation of mechanical energy. But this is true for any forces, not just for conservative forces. And then the second one is what we call the impulse momentum relation. Which is that the change in momentum is equal to the integral of a force, the net force really, dt. Okay. And by the way, this is just the integral of the net force on a path, dr, by tr. So classical work energy tells you that the change in kinetic energy is equal to the integral on a path. In other words, this is force times distance. If the path is straight and the distance is straight.
Mm-hmm.
Whereas the change in momentum, that's the integral of a force over time. So this is just force times time. If the time is constant, the force is constant. If the force is constant, then this just becomes F delta T. Okay.
Okay. That makes sense. Thank
So,
you.
right. And these are really useful. Like you'll see a problem where you say, oh, I need to figure out the final velocity. And then you go, oh, but I can't. And so you'll say, I want to use conservation of energy, conservation of classical energy. But then you'll notice that some of the forces, so maybe a key force is not conservative. That messes you up. You can't use conservation. Maybe you can't use conservation of mechanical energy because a force is not conservative. But you can always use conservation. You can always use the classical work energy theorem, even if the forces aren't conservative. The other thing is sometimes I will ask you for this thing, and you won't have to bother doing this integral. You just look at that. Same way. Sometimes I'll ask you for this thing or that thing, and again, you won't have to bother to do an integral. You just go to the other side and tell me what it is. Kind of like F equals ma. If I ask you for the net force, don't give me all the forces. Just give me ma. Okay, is that helpful?
Yeah, thank you. That was really helpful.
Sure. Any other questions for today? I will immediately post the correct solutions on the Canvas page after we're done here. I just have to wait for the video recording to transcribe, and then I will post the solutions. All right. Tomorrow, we will spend most of our time doing an in-class exercise where I give you some practice problems, and you get to figure out which concepts apply and which ones don't. And also tomorrow, we will look at one more force, which is, I think we're doing, I can't remember. We're either doing gravity tomorrow and starting with systems the day after, or vice versa. And now you have everything you need to do the fifth homework, which is due on Wednesday. It's a short one. Going once, going twice, all gone. Talk to you guys later. Bye.